So good morning. So we are going to discuss millimeter wave antenna. So in this today's video lecture, we are going to discuss about millimeter wave antenna. So before we are going to millimeter wave antenna, we are supposed to know about the antenna characteristics. So what are the antenna characteristics? Antenna beamwidth, maximum possible gain to Q. Q is nothing but quality of pattern. Then third one, polarization. So what are the antenna characteristics? Antenna beamwidth, maximum possible gain with compared to quality. Then third one is nothing but polarization. Antenna beamwidth. What is meant by antenna beamwidth? So in this diagram easily you can able to understand. Here we are going for side lobe and then main lobe. So in between we are going for half power beamwidth. So with this here we are going to calculate the antenna beamwidth with the help of a main lobe and then side lobe and then power of a beamwidth. The radiation pattern of an antenna is essentially the Fourier transform of its aperture illumination. In a radiation pattern, cuts containing the direction of maximum of a lobe, the angle between two directions in which the radiational intensity is one half the maximum value is known as the half power beam width. That is HPBW, half power BW. See, you can able to see in between the main lobe and the side lobe, in between the two direction, the angle is going to be measured. In radiation pattern, the cut containing direction of a maximum of a lobe. The angle between two directions in which the radiation intensity is one half the maximum value, so that it is going to be known as half power beamwidth. It is commonly referred as a 3 dB beamwidth. 3 dB because here we are going in terms of an decibel. The beamwidth of an antenna is a measure of its directivity and is usually defined by the angle where the pattern drops to one half of its peak value, which are known as the 3 dB point. So the beam of an antenna is going to measure the directivity and it's going to define angle where the pattern which is going to be drop of power of its peak value, which is going to be known as 3 dB point. For a circular aperture antenna of a diameter d, if the antenna is uniformly excited, its beam width is about 70 waves per diameter. The next lobe in the pattern, usually called the first side lobe, will be about 1 divided by 20, that is 13 decibel less of the value of the main lobe, and any side lobe that are further away will be of even lesser value. Because 1 by 20, so obviously it is going to be a lesser value. The rate of decay of the side lobe is an important parameter in any antenna application and is used in many international standards as defining parameter of antenna performance. So the important parameter is nothing but antenna application is going to be used for standard in order to defining the parameter and the performance of an antenna. In general, the maximum gain can be approximately with the formula G is nothing but gain 20,000 divided by beam width half and then beam width D. So the D is nothing but vertical, H is nothing but horizontal. So it's BWH into BWD. So bandwidth of horizontal point of view and bandwidth of vertical point of view, which will result in maximum gain. Next, maximum possible gain to Q. As I said, Q is nothing but quality factor. Quality factor of an antenna is an important overall parameter specifying the antenna performance and the inherent physical limitation of antenna type. Quality of factor Q is going to be an important and overall parameter specifying the antenna performance, and it's going to limit the antenna size also. In particular, a high value of Q means the large amount of reactive energy are stored in the near zone field. These in turns imply large current, high ohmic losses, narrow bandwidth, or frequency sensitivity. Once we are going to have quality of factor Q, which is going to be high, so mean that here we are going for large amount of reactive energy which is going to be stored. How it is going to be implied means large current, high ohmic losses, narrow bandwidth, and large frequency. So knowledge of the antenna Q leads to a responsible, definite assessment of antenna performance because of its clearly physical application. So you should know about the Q factor, that is quality factor, which is going to be lead in reasonable way of an antenna performance because it will clearly give the physical implication. In millimeter wave application, we need to maximize the antenna gain as well as bandwidth. Millimeter means the size is going to be in terms of the milli, so that here we are supposed to see the maximum antenna gain as well as maximum bandwidth. Therefore, it is important to optimize the gain to quality factor ratio in antenna design. It is clear that the optimization of the gain to Q ratio will yield a greater minimized Q than the minimum possible Q, since it demands that the gain be maximized at the same time. So, wherever the Q is going to be a major role, because with this quality of factor we can be able to design the antenna. Once you are going to design the antenna, it's going to give the clear-cut picture according to the optimization of the gain to quality, which is going to be minimized greater than the Q and minimum possible Q. Q is equal to omega W1 P1. So W1 is nothing but time average energy and P is nothing but power. For a second, in free space, the energy radiated by an antenna is conveyed by a transverse electromagnetic wave that is comprised of electric and magnetic field. We are going to talk about the polarization. See, in this diagram, we can able to see A as the P. A is nothing but direction of the reference polarization. B is nothing but direction of the cross polarization. So, in this slide, we are going to discuss about polarization. In free space, the energy radiated by any antenna is conveyed by the transverse electromagnetic wave, which is going to be comprised of both electric as well as magnetic field. So these fields are orthogonal to each other and also orthogonal to the direction of propagation. These fields are orthogonal to each other as well as orthogonal direction of propagation. Orthogonal to the direction of propagation. The electric field of the electromagnetic wave is used to define the polarization plane of the wave and therefore describe the polarization state of the antenna. electric field or the electromagnetic wave, which is going to be used in order to define the polarization plane of the wave as well as polarization state of the antenna. For this purpose, here we are going for electric field. Then this wave is said to be linear polarized. Then two independent linear polarized waves at the same frequency therefore exist and propagate along the same path. Why? Because here we are going for two independent linear polarization, the same frequency. Obviously, it can able to exist and it can able to propagate in the same path. So these future can used for many decay in free phase link, which utilize the frequency reuse in order to double the capacity of a link for a given bandwidth. In this case, each polarization carries different information and is transmitted and received independently. That was the last. When the two polarizations carry the same information and the two components possess specific phase relationship with each other, we can construct a waveform in which the electric field vector rotates as wave propagates. When the two polarization carry the same information and two components are going to possess specific relationship with each other, obviously we can construct a waveform in which the electric field vector rotates as the wave propagates. If the relative phase of two components is fixed at 90 degrees and the amplitude of the components are equal, then the electric vector describes the circular as the wave propagation. If it's going to be 90 degree and the amplitude is going to be equal, then it is going to be a circular. That is going to be named as the circularly polarized. Right. The sense or hardness or handness of the circular polarization depend on the sense of ratio. The sense or handness of the circular polarization, which is going to be depend upon the ratio. In general, two linear components of the propagating wave can have arbitrary phase relationship and also different amplitude. Such waves are said to be elliptically propagated. So in this diagram, you can able to see the propagation of elliptical polarization. If we are going for different amplitude and then phase relationship, then it is going to be known as elliptical polarization. Fully emitter wave. We can present an overview of a fully emitted wavelength technology approach that offers the significant promise of enabling gigabit per second wireless communication rate. We will describe and discuss the requirement of the system component of a 60 GHz free space point to point. So for this purpose only here we are going for. So we can able to present an overall millimeter wave antenna technology that's going to be offer significant in order to enable gigabit per second. There means in wireless communication. Okay. Then we can describe and discuss the requirement for the system component of 60 GHz free space point to point. Constraint. The first constraint is that 60 GHz channel is lossy but is otherwise fixed. The first constraint is 60 GHz. The excess loss at 60 GHz is approximately 15 dB per kilometer, and we need to provide means to overcome oxygen observation and ensure that sufficient margin exists to overcome other losses such as rain-induced fading. So excess at 60 gigahertz is approximately 15 decibel per kilometer. So these losses are going to be considered, and we need to provide a means to overcome oxygen absorption and ensure the sufficient margin exit to overcome other losses also, such as rain-induced fading. We should not think about single point of, we should think about multiple points. Loss plays major role. Loss will be occurring different point of view, different ways, different way. However, we can compensate by increasing the transmitter or receiver gain antenna, and we can go for an example, use directional antenna gain to substitute for the raw transmitted power and receiver noise figure. So here we are going to compensate by increasing transmitter as well as receiver gain. And also we can go for an usage of directional antenna gain to substitute for the raw transmitted power and receiver noise figure. The second constraint is that there is a strong multipath effect in an indoor environment. In other words, the line of sight signal and reflected wave will arrive at the receiver via different paths. The second constraint is nothing but it's going to be affected by multipath propagation. Multipath propagation means the signal will be arrived to the receiver with different paths and different time. This will be a second constraint. When the path difference is n, lambda by 2, there is a restrictive interference between the signal and is called a notch in frequency. So we are supposed to consider the path difference in terms of n lambda 2. It will destructive the interference in between the signal and its frequency. Third constraint, there is a space limit for portable device such as handset. It is essential to know how much the gain we can achieve for an app. So third constraint is nothing but it's going to be a space limit for portable device. Portable device means here we are going to use an electronic output which is going to be applicable for only certain limit, so that you should know about the fourth. We have the problem of noise and interference. The reliability of the communication link is defined by the signal to noise ratio. Fourth constraint is going to be noise and interference. And also it is going to be defined by SNR, that is signal to noise ratio. In a general sense, any undesired power appearing in the communication channel noise and degrades the performance of the link. There are various sources of noise which can be due to environment radiated or generated by equipment in the transceiver. Fourth one, noise. This noise can able to appear in various ways. Noise. The communication channel is noise, degrades the performance of the link, and also the various source of noise which can be applicable in environmental radiation, or it can be generated by the equipment in. Finally, the wireless link can be interrupted by blocking objects which introduce shadow loss. To avoid the shadow loss, beam steering function or multi-beam antenna can be considered. The final constraint is nothing but blocking object. It will introduce a new loss called nothing but shadowing. In order to overcome the shadow losses, we can go for beam steering function, or we can able to go for multi-beam antenna. Path loss and antenna interference. For a wireless local area network, that is nothing but LAN, it is generally assumed that signal arriving at the receiver of many copy of the information carried in the picture have been generated by scattering and other entrainment process. So for a NAND, it is generally assumed that signal arriving at the receive consists many copies. Why? Because it is due to scattering and then other entrainment process, it will be going for many copy of the information carried. Each path will have a specific delay and arriving time which vary according to the dimension of the entrainment. As I said, path lag is nothing but they should reach close to destination with that specified path and then without any time difference. Here, due to the path lag, it will go for a specific delay and then arriving time. It will vary according to the dimension of the entrainment. For a specific path, that in the diagram what we have been given in this slide, the delay profile of the channel is determined by the delay time, path gain as well as phase of each path. In order to reduce the multipath effect, it is usual to receive each path and its corresponding time shift in order to maximize the received power and reduce the signal distortion. So here we are going to reduce the multiple path effect. It is usually to receive the each path at its corresponding time shift in order to maximize the received power, and here we are going to reduce the signal distortion. It is usually necessary to reduce the effort of major paths which have most power. So this will be in part. Next, we are going to identify the solution. To compact this effect, we need to focus or direct the radiated power from the antenna in given direction. So this will be a first solution. The power flux density in that direction will be greater than if omnidirectional antenna that used to transmit the same power is called antenna gain. The power flux density in that direction will be greater than if an omnidirectional antenna were used to transmit the same power is called antenna gain. On the other hand, the degree to which the power is confined is called directivity. These two quantities are closely related by the radiation efficiency of an antenna and can be expressed as follows: gain is equal to efficiency into directivity. Directivity means the degree to which the power is confined. Efficiency, it is going to be an output. Once we are going to multiply efficiency and directivity, we will get the gain. A typical antenna is able to couple energy to and from free space with an efficiency approximately equal to 55%. The usual approach to establish the power received by an antenna is to consider an isotropic radiator transmission power PT, so that this power is distributed over the surface of an expanding sphere as the wave propagates. Power is distributed over the surface of an expanding sphere as the wave propagates. At the receiver, power flux density is then PT divided by 4 Pi R square. R is nothing but distance between the transmitter and the receiver. The received power is then determined by the effective aperture AE of the receiving antenna, so that we will be getting the received power PR equal to AE PT. AE is nothing but the effective aperture. PT is nothing but power transmitted divided by 4 pi R square, that is nothing but area. So finally, G is equal to 4 pi effective aperture divided by lambda square. Lambda is nothing but S. Antenna. Fabry square root it is FPC antenna. It could be excited by a single source located inside the cavity, such as coaxial probe, a microstrip patch, a swat in this ground plane, or waveguide on. It hosts a dual polarized array with press NMR. See, here we are going for space, phase 1, phase 2, phase 3, n number of n space. Here we are going to have array, that is dual polarized array with press NMR. Once we are going to finally look this one, looking like second image. Ray optical and weakly wave model. So it was shown that a highly directivity beam in this class for antenna is also produced by an excited weakly wave with small attenuation constant and broad phase velocity. So by the diagram itself you can able to clearly understand this class of antenna is produced by an excited weakly wave with small attenuation as well as broad phase velocity. The Leakley wave model of was compared with a ray optical description. It has been clearly given in the diagram. See, first one, A is nothing but ray optic field, B is nothing but weakly wave field. Ray optical you can able to see from the source by using the substrate. It's clearly going. The same thing if you are going to consider this weakly wave field with the source and the substrate, there is an leak with small attenuation constant as well as phase velocity, large phase velocity. So due to this, it's going to be named as a weakly wave model. High directive and high gain antenna. One of the method of achieving high directivity and high gain in a small size involving combining a planar antenna with 3 dimensions. So here we can able to see clearly. It's going to consist of an antenna. It's going to be a 3-dimension one. With this, you can able to go for ground. We can go for front. We can go for back. So with this, we can able to clearly combination. A dipole antenna can be combined with a horn antenna. See, in center you can able to see that is nothing but a horn antenna. After that, here we are going for dipole antenna. The dipole antenna can be combined with horn antenna. Similarly, a patch bed horn antenna has been experimentally investigated at microwave as well as millimeter wave frequency. These also we can. The result that for the result indicates that for a 70-degree flare and angle on horn aperture from 1.0 lambda to square to 1.5 lambda square with the dipole position between 0.36 to 0.55 lambda. Yield good radiation pattern with a gain of 10 to 30 decibel to 10 to 30 decibel at 60 gigahertz and cross polarization level lower than 20 dB on both sides. Combination 2 in figure 4.6 it has been clearly shown the array length that a lens fed by multiple slot can radiate multiple beam with a minimum of 3 dB level of overlapping between the array. The coverage of the lens antenna system has been optimized through the utilization of multiple slot arrangement leads to a broad band coverage. The third one, the multi-beam lens antenna is suitable for an indoor wireless access point or for use as a switched beam horn antenna in the communication. So in array lot here we are going for array, in between here we are going for lens. So with this here we are going to go for multiple slot arrangement which is going to lead a broad band coverage. The multi-beam lens antenna is suitable for Combination 3. It is also possible to excite a circular horn antenna with quasi-Yagi antenna. Single mode operation is achieved by placing the circular waveguide. The measurement antenna gain and the radiation pattern of the longer horn corresponding to optimal horn characteristics with a waveguide. The integration of a quasi-Yagi antenna with a horn makes this antenna a symmetric to portable devices. The edge diffraction from the incoming horn aperture is reduced, which can be of use in encouraged horn. The single mode operation of the antenna allows the integration of the polarized directly at the aperture. Beam steering. The multi-phase represents as a delay that differs by lambda divided by 2. When the data increases, the symbol length decreases due to multi-delay spread. To overcome this issue, pre-steered antenna reduces the spatial extent of the signal and resulted in improved multi-path processing. Need of switched beam. A single antenna is emitted with an antenna height more than 30 with half power. This, as we seen, is due to movement of the people who easily block and attenuate. To overcome this problem, here we are going to implement a switched beam antenna array or adaptive antenna array. The array is subsequently required to track the signal path either continuously or periodically. So that here we are going to use need of switched beam antenna. The many type of antennas actually are considered to be unsuitable for engineers. In addition, it is also necessary to operate a 60 GHz antenna with appropriate transmission gain. The beam steering can achieved by this use of either switched beam array or phase array. Their implementation is much easier than the phase array, which requires the capability of continuously varying the progressive phase shift in the element. 2x2 beam steering antenna. So by the diagram you can able to see 9 units of 2x2 horn antenna. The complexity of phase array at the 60 is typically limited by the design requires a multi-bit phase shifter and to generate good polarization. By adding several vital horns, this design can attain under the situation. The steering network needs to have the correct amplitude and phase in two orthogonal linear propagations. The main challenge is to design to reduce the side lobe result optimal 2x2 element. So this will be a comparison of 360 GHz antenna design, 8x8, 4x4, 2x2. But high gain 8x8, yes, 4x4, yes, 2x2, yes. Half power beam width 20 degree, yes, yes, yes. Side lobe 10 to minus 10 to minus 20. Difficulty in 8x8 phase, it is going to be applicable in 4x4 beam array. It is not easy in 2x2 array. Circuit polarization medium in 8x8, possible in 4x4 or in 2x2. Beam steering. Beam direction is controlled by phase shifting. Beam direction controlled by switching. Beam direction controlled by horn. Feeding point. Amplitude phase in 8x8, 4x4 amplitude, 2x2 amplitude and phase. Design is going to be complex in 8x8, no in 4x4, 2-bit in 2. Challenging. 8x8 is going to be a complex phase shifter. 4x4 which is going to be a high gain, small size. With 2x2 the side lobe effect. So that's all about millimeter. I hope you have enjoyed the video lecture. So that's all about the